brand new integral technique. If we look at these three examples, we don't know how to integrate these yet. That's why we're going to learn some new notes. Integration by parts involves this formula, uv minus the integral of v du. I'll talk about in a little bit where that formula comes from, and I'll show you why I'm choosing things for these steps there. For the first example, I just want to go through the nuts and bolts, show you how it works, and then we'll talk about why I chose some things. We'll talk about where the formula came from. Typically, we don't have an issue knowing when to use integration by parts. Typically, you'll have like a normal thing times like a weirder thing, and then a normal thing times a weirder thing. Or if you have an ln in the problem or an arc trig function in the problem, it's not a simple u to u like we made those in the past. We got to use integration by parts. So it'll be using a couple other instances as we go forward there. It might not always be obvious, but you know, typically if I have a normal thing times a weirder looking thing, I know e to the 2x and the sine of x isn't that weird, but relatively speaking, you know, it's a little bit more of a complicated thing there other than just the x and the x squared there. But typically once I see that, then I'm thinking, hey, if it's not a u du, then I'm gonna go ahead and try integration by parts. Like if I have an e to the 2x squared right there, then I would let the u equal the power. That would be a simple u du. It'll match up with that x. But this is not a u du. These are not u du problems there. So normal thing times a weird thing. Let's just see the nuts and bolts part, how the integration by parts work, okay? So what I'm gonna do on this one, I'm gonna let the u equal the x, and then whatever my u is equal to, the dv is the entire rest of the problem, which will be e to the 2x dx. So whenever I smush the u part and the dv part together, that should equal the original problem. So once you choose the u and the dv, here's what we're going to do now. We're going to find the du and the v. So I'm going to take a derivative, and then I'm going to integrate it. So that's what we're getting right here. When you go from the u to the du, you're doing a derivative of that thing. When you go from the dv to the v, you're going to integrate that. So these problems involve doing derivatives and integrals all in the same problem here. So when I do the du, I just do the derivative of the x, which is just 1, and then I tag on the dx like we normally do. And then here, when I integrate the dv to get the v, I have to integrate this to get the v. So when you integrate e to the 2x, you're going to get e to the 2x, but do that balancing in your head. If your u is equal to the 2x, your du is equal to 2, balance that with a 1/2 right there. So let the u and the dv be stuff, and then you're going to take a derivative, then you're going to do an integral. And really, right now, all you're going to do is jump straight to this formula right here. And so the pattern, the way it's going to go, it's going to be u times v. So it's going to be this times this minus the integral of v du. So minus the integral of this times this. So it always goes in this pattern where you go like this thing times this thing minus the integral of this thing times this thing. So if I go u times v, I'm just going to have x times that 1/2 e to the 2x, and I'll go minus the integral, and then I got to go v du when I use this formula. So my v is this 1/2 e to the 2x, and then that du is just equal to 1 times the dx right there. So sometimes you'll have some other than the 1, so you squeeze that in right there. And so usually this part here looks a little bit more involved sometimes, but I don't ever really care about it because I don't have an integral symbol right there, which means I don't have to integrate that. So usually that part just kind of carries down. And a lot of times for this first step, instead of writing it like that, I'll write it just like this, where if I have a constant, I'll pull that constant out right away. And so that sometimes is my first step right there. But so then you integrate this. At this point, you should have something you could integrate. If you don't, then we maybe made something a little bit too complicated right here, okay? But hopefully we have something we can integrate. So I'm just going to integrate this now. So when we integrate e to the 2x, we get e to the 2x. But again, that u is equal to that 2x. The du is equal to 2. I got to balance that with a 1/2 each time I integrate. And then this 1/2 is already there. So that's going to carry down and become a 1/4. And then we get this for the final answer, and then we're done. Now, the back of the book does some weird things. They get common denominators and stuff over the place. A lot of unnecessary work there. Make sure you access my link for the answer key for this section there and just use that to kind of check your answers. All right, and then I just want to stress, if I take the derivative of this stuff, we will get that stuff right there. Now, let's show you where this formula comes from in case you're a little confused what's going on there, okay? The formula is a direct extension from your product rule, okay? So just ignore the orange marker for a second. This means the derivative of u times v. And then that black marker, that's our product rule. I did first function times derivative of the second plus the second function times derivative of the first. So that's something true in the black marker. It's just your product rule. And then what I'm going to do now is take that product rule and I'm going to integrate both sides. I'm going to integrate everything here. So if I integrate that, when I integrate the derivative, that just gives me that original function. When I integrate that, I get the integral of u, and I just rewrite the notation. Instead of using the prime notation, I'm going to use the dv notation, and I have the integral of v, and then rewrite that notation, use the differential, the du notation. And then right here, notice if I solve for this integral right here, I just take this, the integral of v du, and I subtract that to both sides. So then I get that integral is equal to that uv minus that integral of v du. And so that's our formula right there. That's where it's coming from. It's just a direct extension of that product rule and maneuvering that stuff around a little bit. So what we're going to do is a very powerful thing, because we take things that we can't integrate and we break it up into parts. We break it up into a u part and a dv part. And then, so that's our formula that we use. So once we break it up to a u part and a dv part, instead of doing something that we can't integrate it, we use this formula, this uv minus integral v du. And our goal is hopefully we turn it into something that we can integrate it, like we did right here. So I couldn't integrate it, broke it up to a u part and a dv part, and then that integral of v du part, it turned it into something that we can integrate right there. Okay, now let's do, what I want to stress now is, so we got the nuts and bolts, the steps, how that works out there. So it's really not a difficult concept there, just sometimes the problems get a little bit lengthy right there, but it's usually just follow the steps there and use a formula. Let's talk about why I'm choosing something for the DV. I thought about doing a couple examples first and then talk about that. You probably want to write this down. I'm not going to write all this down, but you probably want to write a couple things down here. The number one thing is the DV. Whatever we choose for the DV has to be something that you could integrate it. So if you let the DV be something, if you look at that and you can't integrate that, or if it looks like a crazy, crazy thing to integrate, then you probably don't want that to be the DV. So usually my rule is I try to let the DV be usually the more complicated looking part of the problem, because it's very useful if we could let the u be the part that goes down in power, like let it equal the x part or the x cubed part or the x to the fourth part, as long as I can integrate that dv. So a lot of times I let the dv be the harder looking part of the problem, as long as I can integrate it, because if I can't integrate it, then that can't be my dv. So we'll talk about that as we go through some examples. Now I just want to stress on this ln of x problem. All right, we'll do this one last. On this ln of x problem, what you know before, if I gave you like the integral of ln of x over x, I always had, in the past, I had to make the ln of x integrals work out with the b. I had to make it be an easy u du. So notice if I let the u equal the ln part, the du is that 1 over x, so we get that 1 over x to match up, and I have just the integral of u du. That's a simple u du. But now if I just give you the integral of ln of x, okay, I can't, that's not a u du right there. So that's where we're going to learn integration by parts. So the thing is, or even if I gave you like x times the ln of x, all right, if you follow that first example, if you try to do this, u equals x, dvb ln of x, that's not going to work, because you can't integrate that. Like if I could, like if I gave you like the integral of cosine, you know, you could go straight to the answer, right? You could integrate that and get sine. We don't have a property that allows us to integrate ln of x to go straight to an answer on, okay? So since we don't have that, what I told you before, when you have an ln, I always said before, when we first learned ln integrals, I said, if you see the ln inside the integral, you have to let the u equal the ln part. That the same thing is true right now. I have to let the u equal the ln part. So that's what I mean by, like, typically I let the dv be the harder looking part of the problem. But if I can't integrate that dv, then that can't be my dv. Okay, so it's not always going to be the harder looking part of the problem. It's not just one magical thing that I could tell you that works on all these there. So what I have to do, the instant I see an ln inside that integral, I have to let the u equal the ln part. All right, that's why I told you in a prior chapter that the same exact rules apply there, okay? Because it cannot be the dv. I can't go straight to the answer and integrate that thing. So I can integrate the ln, but I have to use integration part for heart sign. I got to go a little bit indirect approach. Now, if you see the ln and your u is equal to the ln part, that means your dv is the entire rest of the problem. So the entire rest of the problem then is just the dx part. There's really nothing, you know, left right there. But the dx will always be part of that dv, because we're always going to integrate that. And you know, you always have that dx symbol when you integrate it. So like I said, let the u be the ln part. And then what we're going to do is just take our derivative. So when we do the derivative ln of something, you got to go 1 over that stuff, times it by the derivative of that stuff. And so our du here is just going to be a 1 over x dx. And then when you integrate the dv part, that's just the 1. So you're integrating both sides. So when you integrate the 1, you're just going to get an x. And now we have what we need right there. So I have my u and my dv. I did a derivative, did an integral. So I found my du and my v. And now we're just going to use a formula, uv minus the integral of v du. So we're going to go u times v. So I'm going to go this times this minus the integral of v du. Now, just for note purposes, I just want to show you, I'm taking v times, it says v times du. So I'm going to take my v, which is the x, times it by the du, which is the 1 over x. Then you got the dx right there. And so now you have this x ln of 2x minus the integral. These x's cancel out. So now you just have the integral of 1. And so you have something that you could integrate right there. So when you integrate the 1, you're just going to get an x. And then we're done. If you took the derivative of that, you would get that original problem right there. Okay, I'm actually going to do that one real quick. You kind of fast forward if you don't care to watch that. But if I did a derivative of this, right? If I did the product rule, I'll go first function times by the derivative of the second function. So I would go 1 over that 2x times by the derivative of that 2x plus the second function times by the derivative of the first, which is just 1. And I do the derivative of that x, which is also just 1. So here the 2's cancel out, the x's cancel out. So there's a 1. I have 1 minus 1, and all I'm left with is ln of 2x, which is my original problem right there. So it does work, okay? All right, so let's do one final example. You probably already have an idea on this one that the u part is going to be the x squared, and the dv part is going to be the sine of x. So now before I do anything, and I always put that dx with that dv part, before I do anything, I got to make sure I can do an integral of that dv part. So my mindset on just about all these problems is I try to typically let the dv be the harder looking part of the problem. So by comparison, the sine of x is a little bit more harder looking than just a simple x squared, right? So I try to let the dv be the harder looking part of the problem as long as I can integrate it, and I can integrate that, so I'm good. So a lot of times it is nice to kind of have that x squared be the u part, or that part that goes down in power. It just works out a little bit nicely. We'll see that in the next video as well. But like I said, on this problem right here, if I use that same thing, I let the dv be the harder looking part, I can't integrate that. So that's when I would just have to go back and say, hey, on this problem, that u would have to be the ln part, and the dv would have to be the x part on that problem. All right, so as I look at this, so then we're just going to go through the nuts and bolts there. So once you get your u part and your dv part settled, and again, when I squeeze together the u part and the dv part, it is equal to that original problem. So the du is just going to be a 2x, and then I have to integrate this. So when you integrate the sign, we should know that's going to be a negative cosine. So make sure you know your trig integrals with your proper sign. And let's just kind of see what happens in this one. So now I'm going to use my formula. I'm going to go u times v. So I'm going to go this times this. And I'm going to go minus the integral of v times du. Now, when I go minus a negative, that's going to turn it into plus a positive. And I'm doing this 2x times the cosine of x. So I'm going to pull the 2 out right away, but I still have the x and the cosine of x left on the inside of that right there. All right, now let's take a look at this one, all right? A little bit something different happens there. So when I did my integration by part step here, I got something I could integrate it, so I integrated it, done, right? When I did my integration by part stuff here, I got something I can integrate it, very easy integral, I integrated it, and then I was done. I got my answer right away. Now, as you look at this one right here, you gotta ask yourself, hey, can I integrate this? Now, some of you are seeing it right away. Yes, we can integrate that, but to do that integral, I need to use integration by parts again on the same problem. So that it is something normal that you will do on quite a bit of these problems there. But notice that the reason I know I'm known to use integration by parts, I told you integration by parts is used a lot if you have a normal thing times a weirder thing, something that you can't normally integrate. So I had a normal thing times a weirder thing, normal thing times a weirder thing, normal thing times a weirder thing. I can integrate this, but I just need to use integration by parts. Now it does look a little bit better, right? Instead of an x squared, it does have an x attached to it. So to me, it does look a little bit nicer. You got a real interesting problem in the homework there, because sometimes it doesn't look as nice. I think good luck with like number 35 in that homework there. Do the best you can on that. There's something a little bit special happens on that one. I'm gonna see if you can challenge yourselves there, kind of figure it out, but we might need to kind of talk about that and go through some of the problems there. But anyways, stay consistent. So I'm gonna do integration by parts again. So if you want to keep it neat, you know, very neat, use a different color, whatever there, but I'm gonna let the u be the x part again, and I'm gonna let the dv be the cosine part, and I'm gonna take the derivative, which is 1, and I'm gonna need to integrate this, which is sine, because the derivative sine is cosine, and let's use that integration by parts again. So I'm gonna go x u times v, so x times sine of x, minus the integral of v times du. So sine of x times the 1 is just sine of x. And then, so now I actually have something I can integrate straight up where I don't need. So it does get a little bit better typically when you do that multiple times. So I have this x sine of x carries down. And then when I integrate the sine, I'm going to get a negative cosine. But when I get that negative cosine, I already have that negative out there. So that's going to turn into plus a positive cosine. Now, here's where you got to be careful, especially if you got to do this like 2 or 3 or 4 times. Everything, this 2 that you have in front is in front of all of that stuff. So usually what I'll do, I like to keep it neat. If you have the different colors, you want to use different colors, you can do that, but I like to keep it neat and carry that down. I'm going to put that whole thing in parentheses, everything after that, and this 2 is in front of that. So if I had another integration by parts right here, and I have another set of parentheses, that 2 will be in front of all of that. If I have a number in front of that, I got it in front of all that. So be kind of careful there. Some of you have messy handwriting there, might get yourself into trouble, but be neat with that. Just work your way downward. And so this 2 is in front of all of that. What we're going to do on these problems is clear out the parentheses. I want you to always clear out the parentheses so we're always kind of getting the same answers, you know, in a testing situation. And then this stuff is also going to carry down. So if I distribute the 2 here, and then we're going to remember our plus c, and then we're done. And then I just wanted to mention, like right here, not everything in this section is going to be integration by parts. Like this is an example right here. If you got a single e in the problem, let your u equal that power. See if the u du works there. This is a simple u du, right? Here's a common mistake there. If I give you this x over e to the 2x, this is not a simple u du, because if I let the u equal the power, the du is equal to 2, not giving me that x to match up. So on something like this, what I would need to do is move that up to the top, make it x e to the negative 2x. This is still not a u du, so I have to do an integration by parts on this one. So when I'm choosing what to let something equal, I try to let the dv be the harder looking part of the problem as long as I can integrate that. And so I would do integration by parts. Sometimes I have people take a look at this. They're going to do integration by parts, and they'll let the u be the x, they'll let the dv be the e to the 2x, and that's like what we did on the first example. That's what we did on the first example. So you don't, remember, I just want to emphasize that. I got a note to remind myself there, just if you squish the u part and the v part, the dv part together, that should equal the original problem. So if you let the u equal the numerator and the dv be the denominator, I didn't tell you that. If you squish them together, you don't get that right there. But see, if you let the u be the x and the dv be either the negative 2x, when you squish those things together, that is x e to the negative 2x, which is x over e to the 2x right there. So just make sure whatever you choose for the original u and dv, when you squish them together, that equals the original problem, and you don't want to change that problem at all. So again, try to let the dv be the harder looking part of the problem as long as you can integrate it. But if you got an ln in that problem, you got to let the u equal the ln right away. I think a lot of the homework problems will kind of be straightforward. There are a few in there that just look a little bit crazier, and so you might not be sure what to let the u and the dv be equal to. And then some are just a little bit lengthy because you might have to do it like 3 or 4 times. It's just kind of mild this, be careful with that, be persistent. If you got little mistakes, you know, try to catch all of those on your own and work those out as many times as you need to kind of figure that stuff out there. But on a few trickier ones, we'll have to discuss what to let the u and the dv. If you're persistent enough, there's only so much stuff that you can let the u and the dv stuff equal to. So if you're persistent enough, even on some of those tougher ones, you can kind of figure it out. It's just trial and error, right? Just be persistent, be tough with that, and just try some stuff. And if it works out, great. If it doesn't work out, try something else, right? And get that stuff going for you. Thank you.